All right, subscribers, welcome back to another episode of Science with Surbat. Today what we're going to be talking about is section 5.5 in AP Chemistry. And before we get going, I want to outline a couple of objectives you should be able to meet by the end of this video. So objective number 1, define the terms heat capacity and specific heat. Objective number 2, calculate any one of the following quantities given the other 3, which is heat, quantity of material, temperature change, and specific heat. And then objective number 3 is to calculate the heat capacity of a calorimeter given the temperature change and quantity of heat involved. Also, calculate the heat evolved or absorbed in a process from a knowledge of the heat capacity of the system and its temperature change. So let's get underway here. It's pretty math heavy in this section. And just as a reminder, these yellow highlighted terms are the terms you need to fill in the blank, as well as write what I do in these notes. Okay, so we start out here with calorimetry. And so calorimetry is how we measure heat flow. Remember, it's very hard to measure heat flow directly or take one temperature. And so if we have heat flow, we can take 2 temperatures and we can utilize it in some calculations. The other thing that it allows us to do is find the enthalpy. If we're doing these experiments under constant pressure, then we can find the enthalpy. Now we also need to be familiar with our calorimeter. And so our calorimeter is just a device that we can actually find that heat flow. And again, the whole goal of this calorimeter is to find delta H through the experiments. Now, pictured here, and it's pretty well labeled, pictured here is a coffee cup calorimeter. And you may be thinking to yourself, okay, it's a styrofoam or 2 styrofoam cups, but actually this is very well insulated and it really accounts well for what we can measure using our Hess's law. And what we have here is, again, 2 styrofoam cups and a reaction that's happening in the styrofoam cup. And then we usually, it says a cork stopper, we usually use cardboard, but because it has a lid, it is considered to be a closed system. And we'll be utilizing our coffee cup calorimeters in an experiment. And like I said, it's actually a very precise tool. It may not look like one, but very precise tool we can use when we're trying to find that heat flow or that heat change, ultimately our enthalpy change. Now, what we can get into more specifically is the formula associated with one of these calorimeters. So we get to our next page of notes here, and we start talking about a couple of different things in its heat capacity, and we go a little bit further with molar heat capacity, but heat capacity is just defined as the amount of energy required to raise the temperature of an object by 1 degree Celsius. Now, it may be sounding familiar, this definition, because the calorie had a very specific definition, but the difference between this and a calorie is that this is for any object. So we could be talking about water, we could be talking about hydrochloric acid, the list could go on and on. We are, again, concerned about any object compared to a calorie is just looking at raising that temperature 1 degree Celsius for water. Now we are going to use some specific symbols, and so heat capacity is going to have the symbol of C. And on the flip side here, molar heat capacity is a very similar thing, but it's going to use the symbol C with a subscript M, and it is the heat capacity for 1 mole of that substance. So again, once we find the heat capacity, we can get into 1 mole of that substance here, and we will do that and show you how those numbers differ. Now, the major thing here is specific heat. So each individual compound, each individual element has its own unique value for specific heat, and so it has a unique heat capacity. Now, this is the formula that we are given, but oftentimes it's a lot more helpful if we just cross multiply. So if we cross multiply here, we have Q equals our specific heat times M times delta T. Now, our Q is our heat change, and that is normally expressed in joules. And so I'll put normally here in joules. Our CS is the specific heat capacity of the substance we're looking at. And I want to point out this, that oftentimes, and I'll probably do this while we are going through problems, we can also, instead of just using CS, we can use the symbol C here. And then our M is our mass of our specific item we're looking at or object we're looking at, and that needs to be in grams. Oop. And again, that is in grams, okay? And then our delta T is our change in temperature, and I've said it before, but I'm going to say it again, and we're going to actually start utilizing this in our equation here. Final minus initial is very key to thermodynamic equations or thermochemical equations. So this right here is our final temp, and I'm going to abbreviate temp, T-E-M-P, minus our initial temp, okay? And then I should also add here, the specific heat capacity, I should have put this in units, is usually expressed in joules per gram Kelvin, okay? And we'll get to that here in a second. All right, so we have this. We're going to utilize this in the next problem here as we go forward. All right, so as I mentioned, I said, hey, we're going to utilize that problem, or we're going to utilize that formula for a specific heat problem. So I'm going to, before I even read this, I'm going to write down our specific heat formula. So we have Q equals C times M times delta T. And again, like I want to do in all my equations here is I want to list everything out. So I want to list out Q, my C, my M, and my delta T. All right, so now we are going to read this problem. So it says, how much heat is needed to warm 250 grams of water from about 22 degrees Celsius to 98 degrees Celsius, okay? So the question is asking how much heat that we need here. So this Q is going to become our question mark. Now, the C, the specific heat, is not given, and so oftentimes we will utilize this chart for our specific heat. Now, we are dealing with water, H2O, and the specific heat of water is 4.18 joules per gram Kelvin. And then our mass of water, it says we're using about 250 grams of water. And so we'll put that here. And then our change in temperature here, remember, is final minus initial. So our final temperature is 98 degrees Celsius minus 22 degrees Celsius. So I'm going to calculate that temperature change. And I'm going to add a little bit of detail here to why we can use degrees Celsius. So I get a temperature change of 76 degrees Celsius, okay? Now, you may be thinking, hey, we have units of Kelvin and we have units of Celsius. It is okay to use our Celsius temperature because the difference in temperature would be the same if using or converting both to Kelvin. So I'll pause and write that down. Now, again, if you want to get real specific, and we can, that temperature difference of 76 degrees Celsius would be the same temperature difference here in Kelvin. So we can use that if that makes you feel warm and fuzzy inside. Now we have all the players of the game, and we can plug these values back in. So I'm going to write this here. We have Q equals 4.18 joule per gram Kelvin times 250 grams of water times our 76 Kelvin, which was the temperature difference, okay? So our Q here is just going to be the product of these particular numbers. So we're going to type in 4.18 times 250 times 76. We press enter, and remember, 250 and 76 both had two significant digits, so we're going to round this to exactly 79,000 as our value. So Q equals 79,000. And then the only thing that's left, grams cancel out, Kelvin cancels out, is joules. So we measure, again, specific heat in joules. Sometimes you'll see it in kilojoules, so you might have to convert that to reflect the appropriate specific heat. Okay, so the answer there, again, is 79,000 joules. Now, we get down to the second problem here, and it's related, but it's a slightly different. So it says, hey, what is the molar heat capacity of water? And so what I'm going to start out by writing is just the specific heat, or the heat capacity that we wrote up here for problem 1. And that was 4.18 joules per gram Kelvin. Now, what we need to do here is this. And I'm going to rewrite this. This is going to look better here if I rewrite our first part here. So same thing, but I'm going to, instead of having it diagonal slash, I'm going to have a slash joule per gram Kelvin. Oh yeah, that's better. Okay, so now, if we need the molar heat capacity, we can no longer have grams, we have to have moles. So remember, the molar mass of water, H2O, is 18.02 grams per mole. Okay? Now, we have to think for a second because our diagonal units need to cancel. We're trying to get rid of grams and get into moles. And so diagonally, from bottom to top here, we would have to put grams of H2O. Now, on bottom, we could put moles of H2O. Now, our value here for our molar mass would be 18.02. That number is associated with grams, so we put it as 18.02 grams per 1 mole. Okay, and so now all we have to do is we calculate this out. So we take 4.18 times 18.02 and we divide it by 1, and we get a value there of 75.3 when we round it to 3 significant digits. Now let's talk about units. We have canceled out grams, so now what we have is joules per mole Kelvin, and that's how we would solve for our molar heat capacity. All it's doing is, hey, instead of taking that heat capacity in grams, now we are expressing it in moles. So we had to make that particular conversion. All right, so again, practice is going to be efficient here. The big thing here is, hey, we can use our temperature difference in Celsius. There's no reason to convert it because that temp difference equals your Kelvin temperature, and that makes it really nice and easy for us to do some calculations. All right, so now we can take this equation and we can go one step further, okay? And we can go and we can specifically talk about that calorimetry, or utilizing that coffee cup calorimeter to find out some values, to find out some things about Hess's law, or excuse me, jumped ahead, finding out some things about our change of enthalpy. That's what I meant to say. And we can get into the details here of calorimetry. So we mentioned before, calorimetry is just the measure of heat flow, but how exactly do we do this? Well, we've already viewed our calorimeter, and so what that calorimeter is going to do, it's going to be something that we set up or we put on the tabletop or bench top of our lab, and our lab is going to be at constant pressure. So what that means is our delta H equals our heat change in constant pressure. Remember, delta H, change of enthalpy, equals heat change at constant pressure. Now, what we have here is this. The heat that is gained by the solution is lost by the reaction. Now, a couple of other things too to work through. This formula here is this: C times M times delta T. So if you're thinking to yourself, hey, that looks really familiar, it should, because we just solved the problem. This formula right here is the specific heat formula. Okay, so we've already utilized it, but now I want to be going into a little bit more detail here. So I'm going to consolidate this, and I'm going to say, hey, the Q specifically of the solution is equal to the negative Q of the reaction. That is exactly what this is. That is exactly what this is saying. So what this is saying, I'm going to say this and then pause and write it down, is this. The heat gained by the solution is equal to the heat lost by the reaction. Now, this statement is really important here because of this. The temperature change can be measured via this thermometer, and if we know the temperature change, we can find the change of enthalpy. So basically what the calorimeter is designed to do is, hey, we're going to get some temperature difference, and based on that temperature difference, we can measure the heat flow, which we express as Q, and because Q equals delta H, ultimately we can find delta H. So it's a really useful tool, and it's a really useful application here of finding our Hess's law. Now, let's go ahead and try this out in an example. All right, so we got a lot going on here, so I'm going to read this here. We have a student mix 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH in a coffee cup calorimeter. The temperature of the resultant solution increases from 21.0 degrees Celsius to 27.5 degrees Celsius. We want to calculate the enthalpy change for the reaction in kilojoules per mole, and that should be capital, that should be kilojoules here, okay, per mole of HCl. Now we're assuming that the calorimeter, the styrofoam cups, only lose a very, very small amount of heat. That doesn't make a big difference. And we have a total volume of the solution to be 100 milliliters. And what that is saying is the total solution, and we'll get to that in a second, is 100 milliliters. Now, the density of this solution is 1 gram per milliliters, and the specific heat is that of water, which is 4.18 joule per gram Kelvin. So we have a lot going on here, and so I'm going to break this down into our specific pieces from the formula we just talked about on the last page. That is this. Our heat of our solution, okay, is equal to the heat loss, negative Q, of the reaction. Well, if you've read this carefully, we have the values of the solution. So I'm going to go one step further down here, and I'm going to go to this. The heat of the solution, or the heat gained by the solution, is equal to C times M times delta T. Now, ultimately here, we're going to try to find the Q of the solution. So out to the left here, I'm going to write down Q of the solution. And that's going to be our question mark. Now, our C of the solution is going to be that's listed here in our problem, which is 4.18 joules per gram Kelvin. Okay? And then our mass. If we read carefully, our mass is not given, but we are given the volume of the solution to be 100 milliliters and its density. So if we have 100 milliliters times the density of 1 gram per milliliter, so 1 gram per milliliter, we can do this in our head. 100 times 1 is 100 grams of our solution. So that makes it easy on that. And then our delta T is our change in temperature. Remember, we're always going to have final, which is 27.5 degrees Celsius minus 21 degrees Celsius. Now, that is a difference. Hopefully you can do this in your head. If not, no big deal. That is a difference of 6.5. Just to verify ourselves here, 27.5 minus 21.0. We get a value of 6.5. And we don't need to worry about going from Celsius to Kelvin because we're worried about the temperature change, which would be the same Kelvin versus Celsius. So let's go ahead, let's plug these values into our equation. So we get the heat of the solution to be equal to our specific heat, which is 4.18 joule per gram Kelvin, times 100 grams times our temperature difference in Kelvin, which we found to be 6.5 Kelvin. And all we need to do is get the product of this right here. So we take 4.18 times 100 times 6.5. And we get a value of 2,717. And remember, we only had 2 significant digits. So when we round this here, we would get a heat or a Q of the solution to be 2,700 joules. And remember, our 2,700 joules comes from our grams canceling out and our units of Kelvin canceling out. So now we have our heat gained by the solution. But the question asks, hey, for the reaction, what is it in kilojoules per mole, specifically of HCl? And so I want to talk about this here, this 2,700 joules, or if we're going to get in kilojoules, we might as well do it now, or 2.7 kilojoules. And I want to talk about that number, that value that we just found. And so what's important here is this. This is for the entire solution. We only want one part of this. So I'm going to write that down. So this value here for entire solution. Okay? We only want one part of this, and that part specifically is our HCl. And so I'm going to leave a little gap here between the last part and the bottom of the page. I'm going to write this down. 2.7 kilojoules, the same thing that we have. And now I'm going to talk about this. It says, hey, per mole of HCl. Well, if you're reading the problem carefully, you're probably scratching your head and say, hey, I didn't give you moles of HCl, but I did give you the molarity and the milliliters. With that, we can find the number of moles utilizing our value for molarity, or our conversion for molarity. And so, as a reminder here, our molarity of HCl is 1.0 molar. So if I have 1.0 molar is equal to our number of moles, which we don't know are moles of HCl. We can call that X, divided by our liters. Now, remember, 50 milliliters, and I can write this out to the side, 50 milliliters, if we convert that to liters, divide by 1,000 mils times 1 liter. If I do that here, 50 divided by 1,000, we get a value of 0.050 liters of HCl. Okay? So that is our value here, 0.050 liters of HCl. So all we need to do to find our moles of HCl is just do a little cross multiplication. So we're going to take 1 times 0.050, which hopefully you can see, but if not, 1.0 times 0.050, hey, it equals 0.05. That means we have 0.05 moles of HCl. And so now what we can do is we can plug this value down here for our final value that we get. And before I even put that value in there, I want to talk about this. Remember, we found the heat change or the Q value of the solution, but that's equal to the negative or the heat loss by the reaction. So no longer can we make this positive. We got to make this negative, okay? And that is because we are interested in the enthalpy change for the reactions. That is why we added the negative sign. Now all we got to do here is this. We're going to put this value 1 over 0.05 moles of HCl. Okay, so this is what we're going to do here. We're going to take negative 2.7, and again, it's negative because the positive Q equals the negative Q of the reaction, and HCl is involved in the reaction. So negative 2.7 divided by 0.05. And we get a value here of negative 54 kilojoules per mole of HCl. All right, so I know we took some time here. There's a lot of things that we talked about. The biggest thing here is, hey, what am I given? Can I find the Q of the solution or the Q of the reaction? And then if you have to find the opposite, remember we got to flip that sign because the heat gained by one thing is the heat lost by another, which is ultimately our goal in finding that. All right, so there's one more major concept and problem to go along with this section. And that is known as a bomb calorimeter. Now, so far we've talked about constant pressure calorimetry. This time we're flipping gears here and we're going to constant volume calorimetry. So the big difference here is there is no room for really the reaction to escape, if you want to think of it like that, not so much, but there's no room for the heat to be exchanged with the universe, because everything is contained in this particular device. Now, again, here is our bomb calorimeter. We have a total insulated container. So think of a thermos, a really tight thermos that doesn't allow any heat to go in or out. And this is a lot better insulated than a thermos. And so what this is doing is that we have a sample, we're going to heat it up, and we're going to measure, hey, how much energy was changed or how much heat was exchanged when we heated it up or we put something into this. And so what we need to do is think about our equation. Now, our equation is a little bit different here, and that is because we are under constant volume. So the difference here is this. Because we're under constant volume, we're only going to get negative C under this CAL times our delta T. There is no mass involved in this particular equation, again, because we have constant volume. Now, let's go ahead, let's try this in an example problem, because after you see the example problem, it will make a little bit more sense. All right, so like I mentioned before here, we are going to have the bomb calorimeter formula here. And so I'm just going to write this down where our Q equals our negative CCal times our delta T. And then we'll review what the problem says here. So it says the combustion of methyl hydrazine, formula seen below, is going to produce nitrogen, carbon dioxide, and water. And so now we have a problem here. We have 4 grams of methyl hydrazine combined in a bomb calorimeter, and when this happens, or when it's combusted, the bomb calorimeter increases from 25 degrees Celsius to 39.50 degrees Celsius. In a separate experiment, the heat capacity of the calorimeter is measured to be 7.794 kilojoules per degree Celsius. We want to calculate the reaction of the combustion of 1 mole of CH6N2, or methyl hydrazine. Okay, so we got a lot going on here, and so we're just going to break it down. Okay, so ultimately here, we're going to initially have to find that Q of what just happened in this particular problem. Now, our CCal is equal to that specific heat that is given in kilojoules per degree Celsius. So we have 7.794 kilojoules per degree Celsius. And then our delta T, remember, is always final minus initial. And so our final temperature was 39.5 degrees Celsius minus our initial temperature, which is 25.00 degrees Celsius. So we do this real quickly on our calculator. So 39.50 minus our 25.00. We press enter, and we get a difference of 14.5 degrees Celsius, which, because this is a difference, we can also say this is 14.5 degrees Kelvin. Now, you don't even need Kelvin because our specific heat is given in degrees Celsius. So we're going a little far there on that problem. Now we can calculate our Q here. And so our Q is just going to be negative. Remember, that's involved in the formula, negative 7.794 0.94 kilojoules per degree Celsius times our change in temperature, which we just found to be 14.5 degrees Celsius. And now we can calculate this out. So we're going to take negative 7.794 times our temp change, which we just found to be 14.5. We press enter, and rounding to 3 significant digits there, we get a value of negative 113 kilojoules. And the reason we get kilojoules is because our units of degrees Celsius cancel. Now we have one thing that we need to think about, and that is this. This heat that is given off during this reaction by methyl hydrogen is per 4.00 grams of methyl hydrogen, which has the formula CH6N2. We want it, the problem says, hey, per mole, not per 4 grams, so we need to go one step further. Let me set this up in just a different fashion. So negative 113 kilojoules per 4 grams of methyl hydrogen is the same way as saying, hey, negative 113 kilojoules per 4 grams of that methyl hydrogen, or CH6N2. So we want to get rid of grams and we want to go to moles. So we set up our simple conversion, and again, diagonal units have to cancel out. A little bit different thinking here because our grams are on the bottom, and so we put grams of CH6N2 on bottom, and on on top, and then on bottom we put that per mole. Now, normally I'd tell you go find the molar mass, but to save some time here, our methyl hydrogen has a molar mass of 46.08 grams per mole. 46 number is associated with grams, and so 46 number is associated with grams, and so we put that associated with grams. So I put 46.08 grams per 1 mole. All right, so my calculation, because I have it like this, is going to be a little bit goofy. And so what I'm going to do is I'm going to take negative 113 times 46.08. And that's the stuff that's on top. Now I need to divide it by 4 grams times 1. And so I get a value, when I round it to 2 significant digits here, of negative 1,300 kilojoules per mole. Now, if you wanted to get a little bit more specific here, or you want to be a little bit more clear with your significant digits, this would also be negative 1.3 times 10 to the third kilojoules per mole, again, of CH6N2. And that would be how we find our bomb calorimeter problems, or we utilize that formula. And again, go one step further in finding it, not just in kilojoules per whatever grams given, but kilojoules of moles. All right, so there's been a lot of calculations thrown at you in this episode. Take some time to review these notes, review the formulas and how to solve these, because that will be helpful in solving problems like this in the future. All right, I hope you've enjoyed this video, and as always, if you haven't done so already, make sure you subscribe.